Binary number can be stored in fixed point representation. The magnitude of the numbers stored depends on the numbers of bits used. For example, 8 bits allowed a range of -128 to +127 using 2's complement representation, whereas 16-bit increased this range to -16,384 to +16,383. However, this type of representation limits the range of numbers and does not allow for fractional values. To increase the range and to allow for fractions, we can look to the method used in the denary number system. For example, this number can be written as 3.1211 into 10 raised to the power 23, and this is called scientific notation. If we adopt this system in binary, we get mantissa into 2 raised to the power exponent, where m is the mantissa and e is the exponent. This is known as binary floating point representation. In our examples, we will assume a computer is using 8 bits to represent the mantissa and 8 bits to store the exponent. A binary point is assumed to exist between the first and second bits of the mantissa. Again, using binary as our example, a number such as 0.31211 into 10 raised to the power 24 can be written as converting binary floating point numbers into denary. Example number 1. Convert this binary floating point number into denary. The number is given. As we can see, 8 bits have been reserved for mantissa and 8 bits for exponent. The fraction point is lying after the first bit of the mantissa. Write the mantissa as 0.1011010. The exponent is 4, so move the binary point 4 places to the right to match the exponent value. This gives 01011.010. Convert the whole part of the binary number and fraction part separately. It will give us 11.25 of decimal. In previous example, we have seen how to convert a positive floating point binary number into denary. Let's see another example in which we will see a negative floating point binary number and we will convert it into denary. Now the number is given. In this binary number also, 8 bits have been reserved for mantissa and 8 bits for exponent. As we can see, the first bit of the mantissa is 1, which is showing that this is a negative floating point binary number. Since the mantissa is negative, first convert the value using 2's complement. So write the mantissa as 00110011 plus 1. That will be equal to 00110100. This gives minus 0.011010. The exponent is 12. So move the binary point 12 places to the right to match the exponent value. This gives minus 00110100000000.0. Now convert the whole part of the binary number and fraction if present separately. This gives minus 1664 of decimal. Converting denary numbers into binary floating point numbers. Example number 1. Convert plus 4.5 into a binary floating point number. In binary system, 4 is equal to 0100 and 0.5 is equal to 0.1, which gives 0100.1. Now move the binary point as far as possible until 0.1 can be formed. 0100.1 becomes 0.1001 by moving the binary point 3 places left. So the exponent must increase by 3. Now the mantissa is 01001000 and the exponent will be 0000011. Let's see another example of converting a negative decimal number into a binary floating point number. The question is, convert minus 10.375 into a binary floating point number. Since decimal 10 is equal to 1010 and 0.375 is equal to 0.011, which gives 0.011. But since the number is negative, we need to get the 2's complement of this number. Using 2's complement on 01010011, we get 10101101, in which 10101 is the whole part and 0.101 is the fraction. Now move the binary point as far as possible until 1.0 can be formed. 10101.101 becomes 1.010101 by moving the binary point 4 places left. So the exponent must increase by 4. Now using the 8 bits, the mantissa would be 10101101 and the exponent would be 00000100.